Hi everyone, welcome to this lecture 5th. So today we will discuss about slow-fast dynamics, mixed mode oscillations, canards. Well, I will not give the details of that. There's a lot of theory on that, on works on that. It's just a flavor, but we will discuss that across some works in ODEs, couplet ODEs, or PDEs. All right. So, and to begin, well, sorry. So this is the outline of the talk. So first, we will start with the FitzHugh-Nagumo ordinary differential equation, and which is a slow-fast system. This one that I'm going to present to you, it's a slow-fast system. And then I will discuss the propagation of oscillations in FitzHugh-Nagumo, but this time it's a PDE, a reaction diffusion system. We have already seen that, but we will discuss somehow more details about this PDE. Then what we will discuss the basics of the geometric singular perturbation theory, and you will apply it to the FFHN model. And then I will show you some results on a too slow, too fast couplet FHN systems. Finally, I will show you a canard, which mechanism appears in two different models. One is the Leslie-Gower type, so it's a prey-predator model, while the other one it's related to brain rhythms. All right. So let's start with an example of slow-fast dynamics. So I'm considering this equation, right? It's a kind of FitzHugh-Nagumo equation. All right, so you have seen already these pictures, but I will give more detail today. And I will also do some notations on that. So annotate, can I annotate that? All right. So here in green, it's the first nucline. So it is, so this one, I call it f of u. F of u. So here it's v, here it's u, so here it's v of u. So v equals f of u. All right, so here in this green curve, for the points uv in this green curve, the derivative of u is 0, right? And here, so here v is less than f of u, which means that u of t is positive, right? So ut is positive when I am below the green curve. When I am above, the derivative of u is positive, right? So here we have C equals minus 1.5, but in the same way, so V of t will be less than 0 if U is smaller than C, and we will have V of t which will be greater than 0 if U is greater than C. Now look, we have here an epsilon. Epsilon is small, right? So this means what? This means that when I am not close of this green curve here, so ut here from if I start here, my initial condition is here. I will put some other color, right? Let's do it in this one. So sorry, I made a mistake here. Let's so you didn't say nothing, but here ut is less than 0, right? Yeah, here v is greater than f of u, so f of u minus v, which is ut, is negative. In fact, it's not ut, but it's epsilon ut. So that's the point. Now, okay, I start here with an initial condition here. What's going on here? We have that ut is positive, but the derivative here, we have to divide this quantity here by epsilon, so it's a huge number. When epsilon is small, it's a huge number. So Vt is negative, so the trajectory here is going to decrease in V and increase in U, but since I have this epsilon, this derivative is huge, so I go right there. I go straight there like this. Let's do so it's basically here a straight line. So let's do that again. Stuck with that. What's that? Sorry. So again, if I start with an initial condition here, it's basically a straight line. You agree with that or not? So when I started with an initial condition here, I go very fast here until I reach this curve where ut is 0. So here ut is 0. So I can go across because then u becomes negative. So I'm stuck here. But Vt is negative. So I have no choice. I have to decrease here. So and I'm stuck here because ut is huge, is very large, so I cannot escape this curve. So I'm going there, and in this case, well, my stationary point is here, so I'm converging to this solution. So all right, if I start here, this is the same phenomena. I go like this, and then I reach that here, but then Vt is positive. I'm stuck here. I go there, I follow this curve, and then so here you see Vt is positive, but when I quit this curve, then it's very fast, and I go like that, and I come back here, and I go to the stationary point, to the stationary solution. So here, because of the presence of epsilon is very fast here, then it's slow here, then it's fast, then it's slow, right? So we have basically two time scales. When we are outside this curve, the trajectories are fast. Then they reach this null line, and they evolve there, and then they can quit. But if they quit this curve, the trajectory is very fast again, and eventually I go to here a stationary point, or in this case, depending on the value of c, it's limit cycle. All right. Is there any questions with that? No questions? All right.
No.
Okay.
No question.
It's clear. Is it clear?
Yeah, it's okay.
All right. Okay. So now I consider a PDE. So it's a reaction diffusion system. So I have boundary conditions on so I can take it in whatever dimension I want. So the domain can be just a bounded set in R or in R2. Okay, but for example, let's say I'm in R2, I will take C, which is 0 at the center. So for C equals 0 for the ODE, we have a limit cycle. So we have periodic solutions that attract all the initial conditions. And outside the center of the domain, I take a value C0, which is less than -1, which means that the system is excitable. Is it excitable? Why? Because as we have seen, if I start with an initial condition here, I go directly to the stationary point. But if I start with an initial condition here, sorry, I go like that, and then I come back, and then I come back again. So here, you know, the U, it's like it makes an action potential, right? So if I manage to bring the solution here, it doesn't just comes back, it goes there. So it's excitable, right? So we have already discussed that. And sorry. And okay, so depending on the value of C0, I can have um, it might be that, for example, here this will be a stationary solution, or if my C0 it's close enough of the excitability, I will have propagation of waves. All right, but there's several parameters, right? But what may occur in some cases is that in some cases the center cells will do this kind of things here. And this is, you know, you have small oscillations and large oscillations. This is mixed mode oscillations, or MMOs. So you can have these things on PDEs. All right, this is an example. Depending on the value of parameters, you may have different behavior here. There's a lot of things to study in this PDE stuff when C here is depending on X. Okay, it's just to say that you can have apparition of mixed mode oscillations in PDEs which have a slow fast component, right? I just wanted to mention that. All right, so now I'm going to spend some time in this system. So as a general in a general setting, I consider a two-dimensional system. I call it X and Y. There is a small parameter epsilon, and with a function f and a function g, right? So here I'm going to follow a little bit the introduction of this article, right? So you can find it, and I'm giving some elements which are very well known. I'm not going to give you all the details of that. It's a hard work. I cannot talk you of that in 10 minutes. It requires some personal work to get into that. But let's go. And so I'm giving you the basics of geometric singular perturbation theory. So which will in some way which gives a theoretical justification of my introduction with the FitzHugh-Nagumo model, right? So let's go. Now I'm going to share a whiteboard. All right. Okay, so let's consider this equation. Okay, so epsilon is small, right? I told you that. So epsilon in in this problem is small. So why not take it 0, right? I just put it 0. What do I get? What do I get? I'm listening to you. Is there somebody? You are here?
Yes, nous sommes là, nous sommes là.
So if I take epsilon 0, what do I get?
Si epsilon égale à 0, donc on a qu'une simple équation ici. Ça dit y est fonction de g seulement.
So, but no, I have 0. 0?
Non, on a f égale à 0 et y
Yes.
point égale à g.
Yes.
Oui.
All right. Okay, you can think about what do I get in the example of the FitzHugh-Nagumo. So this will be an exercise for you. But you, while I'm talking, you can just think about what do you get with the FitzHugh-Nagumo equation, right? So, but in the general theory, this system is called the reduced problem. All right. Okay, but now, okay, I want to make here a change of time. So assume the time here is t. So here is so here let's go. So assume here we're working with x of t and y of t, and so I want to make it disappear here. You know, so I can write it here, epsilon dx dt. So I'm going to say that epsilon dx over dt equals dx d tau, right? Which means what? Which means that formally epsilon dt over dt equals 1 over d tau, which means that I have t equals epsilon tau, right? So what do I get? What this one, after this change of time, what do I get? So let's call it now x prime. So the time has changed, right? It's a change of variable. So it's the same. And here, what do I get? So here I add dy over dt. Okay, but now I get, because 1 over dt is 1 over epsilon d tau. So I get all right. So I'm just I'm just taking a little less space for that. Okay, so these two systems are equivalent. I just looked with a different time. And now if I take epsilon equals 0, I get what? X prime equals f of x and y, and y prime equals 0. Okay, and this is called the layer problem. And
Monsieur,
yes,
comment vous avez fait pour passer qu'est-ce qui amène ce problème-là, en fait? Quelle est la raison de ce problème?
okay, you will see.
Parce qu'en fait, j'ai vu tout à l'heure, vous avez écrit y' égale epsilon g de y, g de x, y, et top, vous écrivez ça. Je ne comprends pas.
So I come back. You have this equation here. Epsilon is small, right? So the question is, if I take epsilon equals 0, I should get something which is close, right? Epsilon is very small, so just take it 0. You agree with that? Mr. Cassé?
Oui, mais en fait, epsilon, c'est epsilon is a liar.
No, epsilon is a number. It's a positive number, small. Epsilon is a small positive number.
Epsilon, c'est la dirge, ça représente quoi?
It's a number. You have a ODE.
Okay.
Epsilon is a number. It should be 3, but it will be not 3 because it has to be small. So for example, it can be, depends on your problem, but for example, 0.1, 0.01, 0.000001. It's a small number, right?
No.
So usually it might be interesting to take it 0, because if you take it 0, maybe you will get a simpler problem, right? But there is 2 ways to put it 0. You can just put 0 here, then you get this problem. But you can also make this change of time. You have 2 equivalent systems, and then you take 0, and then you get this problem. So 3 things now. So let's start with the layer problem. So the layer problem is it's prime, right? No, it's 0, sorry. So I need to mute you because we're doing some noise. Okay, so you can just study that. Huh? So what are the stationary points and their stability. Okay, so I'm telling you the
Juste,
stationary.
ça c'est au voisinage de epsilon égale 0.
This is for epsilon equals 0 here.
Au voisinage.
No, epsilon equals 0. I
Parce que
changed.
tout à l'heure, vous avez fait un cas particulier et où vous avez dit lorsque epsilon égale 0, f égale 0.
No.
Donc, c'est pourquoi je me demande si est-ce que c'est ça, c'est au voisinage.
No. You have epsilon which is small. So to understand what's going on, you can take epsilon equals 0 because epsilon is small. So the dynamics must be almost the same for epsilon equals 0 or epsilon small.
Okay.
That's the idea.
Okay.
In fact, there's some tricky things in there, but that's the idea. That's why we are doing it. Okay, now you get that. This is the layer problem. But so I'm telling you that the stationary points, and depending on the stability, gives you what's going on the fast time. Basically, if things are okay, the trajectories are going fast to the set of the stationary points. We'll come back to that. And you have the reduced problem. The reduced problem gives you what? Gives you, it's an ODE, but it's an ODE which lives in a manifold or in this set. So it's an ODE, but it lives on this set. And let's us assume that you can write, for example, y equals phi of x. If you can do that, then you take the derivative, you get y prime equals phi prime of x prime, and then you can just take the equality between these two, and you get phi prime x prime equals g x. So now x phi of x. Okay, now I'm asking you to solve an exercise. Okay, so what's the exercise? So layer problem. Find the layer problem in this case. What are the stationary points and the stability? And yeah, that's it. And then also, what's the reduced problem? And then can you find an equation like we did here, phi prime x x prime equals gxy. In this case, okay. So sorry, it's not a y, but it's a phi of x. Well, so here it's a phi of x. All right. So we are going to start with the layer problem. So the layer problem writes so here so if I look to the stationary points, so the second row is always 0. So I only have to solve this equation. So the stationary points lie on the null line, on the first null line. So those are the stationary points. So the UV such that, all right. Now what I'm going to consider is, so for fixed, so now what I'm going to consider is for fixed V, for fixed V. So if now if I look at the system, so when V is fixed, I have to consider this equation. So in fact, for every given V, I do have that my U is solution of this equation, right? So I obtain here an ordinary differential equation of dimension 1, right? And then I can study the stationary, the stability of, so for a given V, here, I have, for a given V, I have either only one U, which satisfies this equation, or 3. So for a given V, I have 3 corresponding U in this set, either 1 or 3. And then I can look at the stability of the stability of the, for a given V, for a given V star, I get 1 or 3 U stars, and I can look at the stationary solution. So to do that, I just look at the derivative here of let's call it h of u for a given v star, and I take the derivative with respect to u, and I get what? I get 3, 1 minus u star. So what do I get? I get, if u is either less than minus 1 or greater than plus 1, the stationary point of this one-dimensional equation is stable, and if it belongs to minus 1, 1, it is unstable. So now this means what? For given v, here the dynamics of this equation are like that. Here this the stationary point here is stable for fixed v. This one is unstable, and this one is stable, right? So for a given v, I look at the one-dimensional ODE in u, and I got that this one here is stable, this one here unstable, and this one is stable, and so on and so forth. So now I get that. The set for which, so consider the set of I consider the set, let's call it S0, is the set of u and v such that v equals f of u. And within this S0, I consider S0a such that and the same here. So A is for attractive and R is for repulsive. All right, so what do I get? So again, I do that. So here I have that. So this picture gives you what's going on when epsilon is small, right? So the trajectory is here. If I am not living in this manifold, so this is called the critical manifold. This is called the critical manifold. All right, and so you have a theory which says that if when the parts for which so the parts for which this f prime is not 0, then you can, there's the theory, so it goes back to Fenichel, which says that the trajectory for epsilon small will look like that. So my layer problem gives you the dynamics for epsilon small outside a neighborhood of the critical manifold. And then you can study. So that's the first part of the exercise. Then you have the reduced problem. Then the reduced problem is what? Is you get 0 equals minus u cubed plus 3u minus v, and vt equals u minus c. So this gives you so this tells you that now you're considering a dynamical system which lives within this manifold, right? So let's say the my C is here. So my dynamical system lives here, and for example here the Vt is negative, so I will go like that, right? Also here here my V is now positive. So I'm going like that, and here I'm going like that. And so now I can, the last thing that I asked you to do is to take the derivative on the first row. So this is my phi of u. So it's f of u here, but that was also my phi. So I will get here f prime u ut equals, so sorry, it's u minus c and not, right? And so I get that, and ut equals u minus c divided by f prime of u. All right, so when I reach here, this point, when f prime of u is 0, my derivative is no longer defined. So yeah, and formally here I get ut equals plus infinity. So these points here are called folded points, and they are not, their dynamics are not explained by the classical Phoenicial theory, but they have been studied, and basically you have an exponential contraction from, if you take here this distance here, there will be an exponential contraction between this distance here and this distance here. So by saying that, the solution here is going to do that. Okay, and so this gives you the theoretical explanation that I started with. Okay, another problem is when my C is around here. So when my C is around here, so here it's negative, but here it's positive. Okay, and so here you may find some solutions that will still live here and go like that. I'm doing it in red. When C is around -1 here, you can have some of these solutions. And so they call it a canard. And canard because, you know, it's a canard with this head, the head of the canard. And so this goes to Benoit. Goes back to Benoit, 1981. All right. All right. So this is the idea. So now if you want to get more into the details, you can go to these references that I mentioned. And I'm going back there. All right. So you can go, for example, so this one has a very good, introduction, which explains in detail, and it's accessible. You can understand very well with more details what I've just said. This is the canard. The first time the canard was mentioned. So this is the theory, the basic GSPT theory, so financial theory, with the reduced and the layer problem. So there's some things you have. So what does it say? It says more than I say. So it's more theoretical, but it says that the critical manifold, when the derivative with regard to x is non-zero, it stays. So it becomes a slow manifold, right? So differential theory provides the existence of a slow manifold for epsilon close of the critical manifold, and it splits into attractive parts and repulsive parts. And the attractive part will attract trajectories, right? And so this one gives more detail. This is basically about two-dimensional systems, and this is about three-dimensional systems, and it gives you some theoretical results. This is the very minimal. There's a lot much more papers on that, but you can find references within these papers. So now I'm going just to share with you some ideas. So clear all and close that. Okay, now the basic idea of that was that, I come back to the PDE. On the PDE, we found sometimes you can find mixed mode oscillations, but basically you have the oscillatory cells and the excitatory cells. The idea is, why not look at not a PDE, but just two coupled systems of FitzHugh-Nagumo. So this course is on networks and couplet systems. So here you have two. So one FHN and the other one. All right, and they are coupled. Those are the coupling terms. So here you have two nodes, node 1, node 2, and they are coupled by these terms, right? And so of course, so here, so the nodes are not the same, they are different. So C1 is different of C2. That's the difference between the first node and the second node. Basically, C1 will be in an oscillatory state, and the second node will be on excitable state. This is the idea. Sorry. All right. So. Oh. All right. They're here. All right. So I don't know. Okay. Okay, and so I can say, if I come back here, you have here, instead of considering one FHN1 and FHN2, I can also put the fast variables together and the slow variables together, and I obtain two fast, two slow variables, right? Okay, now I can do the same theory. So the theory I explained a little bit for two-dimensional, but you can do it in 4 or more. So you are looking at the critical manifold, which corresponds to the right hand side of the fast part, right? And then the fold line, which was just f prime of u equals 0 in my first example here, it's a two-dimensional one, so it looks like that. And so basically what you can prove is relying on some works that say that you can characterize the dynamics close to the folded points. And so in this paper, it was proven that you have this kind of things, sorry, and this particular bifurcation is known to lead to these mixed mode oscillations. And so here you have these mixed mode oscillations. There's another way to explain that, but I'm not going to talk about that today, because today it's slow fast, right? Okay, now, so we are running out of time. Okay, we consider another equation. This is the equation. So this time, so FitzHugh-Nagumo comes from neuroscience, right? Now, you have here a kind of Leslie-Gower type equation. So this E2 was added by my colleague Aziz Alawi and this and some of his co-authors, and so it's kind of Leslie-Gower equation. So for U is a prey and V is a predator, and they added this term to avoid mathematical singularity, and yeah, which has some biological meaning. So you can refer one of he prepares, which are mentioned in this work, right? So, but here you have an epsilon here also, right? So this means that the dynamics of the predator is much more slower than the dynamics of the prey, right? So I propose you an exercise, but okay, I'm just going to comment that with you. So I recommend you to do the details. So you have some parameters here You have three, actually. You have the A. You have here E1. And you have E2 and the A, right? Okay, so, but I choose the parameters such that, okay, you see that U is an alkaline, right? So U is an alkaline. Now, forget about the U, which is here and here. I take it in front, and what I get the other part of the nucleon is this quadratic curve. And here, if I forgot the V, so V equals 0 is also an alkaline. If I forgot about the V, I have the other alkaline is V equals U plus E2. So you can do the slow fast analysis, right? So when you're here, you get there, and then you get there. It's almost the same that in the FitzHugh-Nagumo stuff. So I recommend you to do the exercise. And then you get there and you reach the critical manifold. So here you can see this will be the attractive part, right? This is the attractive part. And then at some point here, the critical manifold becomes repulsive. All right. Okay. The question is why? You see here, the trajectory follows the repulsive part of my critical manifold. Okay, I will erase some things. You see the trajectory here. Here, the critical manifold is inside, but the trajectory follows it, right? So here we have a canard. Because we follow, this is the definition of the canard, we follow the repulsive part of the critical manifold for a given amount of time, right? Can we compute that? Okay, this was the point of this work, right? So, and okay, so yeah, so you can characterize, in fact, the distance here as a function of as a function of the expression here. So you have basically a function between the expression of the trajectory here and here, and you can make some computations here. So which characterize here the distance, so which characterize the canard, right? Okay, you can find the details here. Then in fact, this was also useful. This is also useful in brain dynamics. There are some typical shapes in the expression of the conductance in assemblies of neurons with excitatory and inhibitory features. It's quite striking. There's a biological works on that. So the U and the V follow some shapes. So there are another things but I'm not going to discuss all the features of that because I just want to introduce a canard phenomenon. And so, yeah, so this equation was proposed to fit some dynamical features relevant in the neuroscience context for conductances. And if so, epsilon actually doesn't need to be small, but when epsilon is small, you have the same type of canard's phenomena here. It's not the same system. It's not the same system. However, this system was set up relying on both FHN and Leslie-Gower. So it's a mix of them. And when epsilon is small, it has it features this canard phenomenon, and it's actually the computations are in fact more simpler than in the Leslie-Gower type. All right, so that's just what I wanted to discuss with you today, and with that, I'm saying you